Okay, now if we want to find the area of this ellipse, we can set up this integral. We can describe the ellipse easily enough. X goes from -2 to 2, and y for given x goes from -3 times the square root of 1 minus x squared over 4 to 3 minus times the square root of 1 minus x squared over 4. And that's because if we solve this for y, we get y equals plus or minus 3 times the square root of 1 minus x squared over 4. We could factor out a 1/4 from here and get 3/2 of the square root of 4 minus x squared, but it's a little more obvious what the limits on x and y ought to be if we use this form. Might be easier to make some changes here, but this integral can be done fairly easily. Okay, but we don't want to do this integral, okay, because it's a little bit nasty. Not bad, but you know, there are things that we just as soon avoid. So we understand that this being an area integral, we could change it to an integral around the path, to a line integral. Now, line integrals are kind of new to you at this point. They're newer than area integrals, so you might prefer to think of an area integral. But looking toward the future, line integrals are often much easier as soon as you get used to them, and they're not that bad. Okay, so what's the boundary of this region? Well, again, this should be second nature. You've been assigned problems of this nature. The boundary could be expressed in terms of the function r equals 2 cosine ti plus 3 sine tj. Now we're getting toward the end of class. I did take the time to write that 0 is less than or equal to t less than or equal to 2 pi in this description. So we could do an integral around this path, which is done in a way very similar to the integral around the unit circle path. Just a couple little differences. You get the 2's and the 3's in there. Okay. What we need is we need the function we're integrating here to be a qx minus py, or minus py plus qx if you prefer. Okay, so what function, what could the p and q functions be such that qx minus py equals 1? Okay, because if qx minus py equals 1, then this integral is of this form and can be translated to this form. Well, very simply, if qx minus py equals 1, we get that really easily if qx equals 1 and py equals 0. For a minute there I thought I'd written q equals 1, and that was not going to be right. So clearly, if qx is 1 and py is 0, we have what we need here. So to get qx equal 1, well, just let's let q equal x. Then qx will equal 1. Derivative of x with respect to x is 1. So qx is 1 and py is 0, and we might as well just get that from letting p equal 0. So if p equals 0 and q equals x, then qx minus py equals 1, and we can translate this integral into this form so that our p dx, well, p is 0, that's 0 dx. Our q dy is x dy. So we integrate this function. And I kind of left the i's and j's out of this, but and I'm not going to bother to correct that. You can just take those two functions and conduct the path integral. Okay, very, very simply done. And that's going to give you the area. Now this is very similar to an example you have in your book. In the book, it's just x squared over a plus y squared over b equals 1. That didn't give you specific numbers. Thought I'd give you an example with specific numbers and give you a parameterization that you can then carry on.